Guten Tag and good day to all. On behalf of Microchip, thank you for your interest in our presentation on how silicon carbide can help reduce the size, noise, and field failures of auxiliary power units used in the transportation segment. I'd like to acknowledge my co-authors Nitesh, Satheesh, and Marc Rommerswinkel. My name is Kevin Speer. The subjects of this presentation are auxiliary power units, or APUs, and the prospects of using silicon carbide in APUs for the transportation segment. We start with a quick brief on the function of a transportation APU and how silicon carbide can help these applications specifically. But before the help can be realized in production vehicles, we need to make sure the technology is up to the task. First, the silicon carbide MOSFETs must be tough. Second, the power package must be designed so that you're not penalized for switching at the speeds and frequencies needed to get value out of silicon carbide. Third, let's say you have those MOSFETs and that package. Where will you get a plug-and-play gate driver with the smarts, speed, and optimization needed during silicon carbide design? Not only will we show you all three of these, but we will show you the three of them together as a total silicon carbide system solution for transportation APUs, only from Microchip. As it pertains to high-power semiconductors, there are two areas of interest on board a transportation vehicle: the traction drive unit, which provides vehicle propulsion, and the auxiliary power unit, or APU, which provides power to all other loads: lighting, heating and air, the power outlets, and more. In the case of light rail, the APU will typically see an input voltage of 1500 volts, necessitating high voltage power devices. With silicon, we know our only choice will be IGBTs. More on this in a moment. Also, the APU must operate continuously and, under most conditions, under a light load. Anything that's operating non-stop begs for the highest possible efficiency. Ideally, these APUs wouldn't be needed at all because their size and weight, especially that required for cooling, takes up space that paying passengers could use. So there's real value in shrinking APUs, which may only be achieved by increasing power density and reducing cooling needs. Finally, the use of IGBTs won't allow APUs to switch at frequencies higher than about 10 kHz, which is a painful high-pitch whine. Wouldn't it be great if we could switch higher than 20 kHz and not hear them at all? Enter silicon carbide MOSFETs. One of the largest, heaviest parts of an APU is the isolation transformer. Because IGBTs have such high switching losses, their switching frequency is limited. This limitation then imposes an all too bulky minimum size on the transformer. What if we could use silicon carbide instead? Compared to the typical 3.3 kV IGBT solution, 1700 volt silicon carbide MOSFETs can help in major ways: slashing switching losses by up to 80% and lower conduction losses at light load, which is perfect for APUs. Heat sinks get smaller and less expensive. Silicon carbide's ability to switch at higher frequencies comes in especially handy, as the ISO transformer will reduce in proportion to the switching frequency. In other words, going from 10 kHz to 40 kHz using silicon carbide could allow the ISO transformer to be reduced by 75% in volume. And as we've mentioned previously, we won't face that horrid audible whine. Alas, nothing comes for free. We understand the possibilities of using silicon carbide, but we must acknowledge the things to be sorted out before one can harness those possibilities. First, are the silicon carbide MOSFETs themselves tough enough to survive the mission profiles of APUs? If yes, how can we possibly realize the benefits of a fast-switching silicon carbide MOSFET if it comes in a package that penalizes you for doing so? And third, let's say you magically have such a power package. Wouldn't it be a dream to have an ingenious digital programmable gate driver that's perfectly matched to not just the package, but to the MOSFET die performance as well? First, let's have a look at silicon carbide MOSFET ruggedness. The ruggedness of the power devices matters a lot to APUs because we expect them to work every time, without fail, or else. So if we want reliable operation for the duration of the APU's service life, as well as the ability for safely surviving common electrical transients, we must verify the suitability of a few key things. the stability of the MOSFET's gate oxide, a known issue of silicon carbide MOSFETs, the lifetime of the gate oxide, the stability of the device's body diode, and failure toughness measures such as avalanche and short circuit withstand time. And what if your power semi devices don't have these ruggedness features? Well, each of these factors, if not taken care of, will lead to increased device temperature and either a gradual failure to creep up unexpectedly in the field, or a dramatic and instantaneous halt of service, leaving paying passengers frustrated and thinking of alternatives to train travel. First up, how stable is the gate oxide? After 1,000 hours of accelerated stress under both positive on the left and negative gate bias on the right, the latter being a particular past problem of the silicon carbide MOSFET, we observe virtually no change in threshold voltage. These are statistically derived data sets on production grade 1200 volt 40 milliohm devices. Should the threshold voltage shift, there will be a noticeable change in the device's performance, such as on-state resistance, which can cause erratic system behavior and, over time, system failure. With a proven rock-solid threshold voltage that doesn't change, you can be confident in the routine, reliable operation of your APU for the designed service lifetime and beyond. Another related concern is the expected lifetime of silicon carbide gate oxides, but we're pleased to report it shouldn't be. We've taken production-grade microchip MOSFETs and accelerated oxide failure using elevated temperature and high electric field. By observing different failure modes in the Weibull distribution, we can calculate the activation energy for each failure mode and then predict the oxide lifetime. As the chart indicates, we've calculated oxide lifetimes well in excess of 100 years at the recommended VGS of 20 volts, even at 175 degrees Celsius. Here again, the integrity of the gate oxide is crucial to ensure reliable operation, but in addition, and as I'll show in a few slides, the oxide integrity can also play a role in surviving electrical transients. Unlike the IGBT, the silicon carbide MOSFET can conduct reverse current using its intrinsic body diode. In some devices, however, this diode degrades over time, causing a higher drop across the body diode and an increased RDS(on), which means more heat than you designed for, and which could result in system failure. Researchers at Ohio State University studied several commercially available silicon carbide MOSFETs. They measured the body diode IV curves and MOSFET RDS(on) after hours of constant forward current stress. One supplier's body diode showed a noticeable degradation soon after restarting the stress. Another supplier showed so much degradation the part became unusable. And the researchers simply stopped testing Microchip's parts after 20 hours because they saw no shift whatsoever. In addition to reliability, this can also reduce cost by saving the expense of the antiparallel diode. So again, you can be confident that your loss profile will remain inside your design window and ensure routine operation for the vehicle's service lifetime. What about unexpected system transients? Short circuit withstand time is a measure of how long the MOSFET can survive the DC link being suddenly shorted across the drain source terminals. In short circuit, the MOS channel is enhanced, meaning the overstressed surge is shared uniformly across the die. This chart shows short circuit withstand time for production grade 700 volt 35 milliohm MOSFETs at various DC voltages and gate voltages. We see that for a 350 volt DC link, the device can safely ride through 10 microseconds of short circuit time at a VGS of 20 volts. Even at a 560 volt DC link, the 700 volt MOSFET can live through 3 microseconds of short circuit time, which is more than enough time for control schemes to come to the rescue. Short circuit, no problem. Avalanche ruggedness is even more demanding. When the load current is suddenly dumped into the MOSFET, not only does the drain source voltage climb all the way to the actual breakdown value, but the MOS channels aren't enhanced, so the avalanche current tends to crowd near the die edge. Talk about hot. First, let's have a look at how our gate oxide stands up. This chart shows time-dependent dielectric breakdown for Microchip and 3 other silicon carbide MOSFET suppliers. For each case, we measure TDDB before unclamped inductive switching, or UIS, and then again following 100,000 pulses. We observed that 3 of the 4 MOSFETs survived R-UIS quite well, and yet Microchip is in a class all its own. Restricting the datasets now to Microchip only, we also see great stability in both RDS on and drain source leakage, indicating that our MOSFETs are indeed rugged to Avalanche and able to safely ride through the most demanding electrical overstress conditions. Rugged MOSFET? Check. Now let's talk about packaging. Imagine getting into a really fast sports car and being told you can't go faster than 100 kilometers an hour. This is what parasitic inductance does to silicon carbide. It looks great and you paid a bit more for it, but you can't drive it the way you know you could. In a power circuit, there are a few primary sources of inductance: common source, power loop, and gate source loop. Whether it's higher switching losses, obnoxious overshoot voltages, or non-compliant EMI, without a low inductance power package, you'll be left wondering what happened to your silicon carbide value proposition. Microchip's latest low inductance package is the SP6LI, inserting less than 3 nanohenries of parasitic inductance into the power loop. For comparison, the source pin of a TO247 alone is around 7 nanohenries. The package is offered in a variety of voltage and current rating, but what's clear across the board is the importance of low inductance at these levels of power. Internally, the design is optimized for gate voltage timing and die current sharing with options of aluminum nitride or silicon nitride DCB ceramics. Externally, the terminals are situated for low inductance connection to the DC link and for ideal paralleling. Also, the base plate is offered in copper or AlSiC. Rugged MOSFET? Check. Low inductance package? Check. It's 2020 for silicon carbide. What else could there be from a single supplier? The third puzzle piece is a gate driver that's smart enough to let you drive that sports car much faster than 100 kilometers an hour and still be in complete control. As we've said, switching at high speeds when combined with any amount of parasitic inductance is going to create overshoot on the gate and drain, and there will be ringing that increases switching losses in EMI. What if there were a way to influence this even further? With Agile Switch's augmented switching, VDS overshoot can be cut by as much as 80% and switching losses reduced by up to 50%. This allows you to buy lower voltage parts and less expensive heat sinks, which is great. Rapid short circuit protection, and as a final perk, you can tweak the programmable gate driver in real time with a click of a mouse, saving hours of time spent with a soldering iron digging through a bucket of gate resistors. Here I show the Agile Switch user interface, where gate drive profiles may be configured, saved, and used at your command. We see this as a conventional profile with a constant 20 volt during the on time, and then it goes to -5 volts for turn off. This is the exact same module in test conditions, except with a slightly different turn off profile. From the 20 volt on state, the user has instructed the driver to go to 0 volts and stay put for 50 nanoseconds, and then to -5 volts to finish turn-off. We do see slight improvements. We reduce the overshoot voltage and switching losses both. While the differences aren't eye-popping, we realize that's in itself a strong testament to the SP6LI's low inductance. We've published other work showing substantial improvements with other package types. The ability to play with these levers and turn these knobs throughout the design cycle with a click of a mouse cannot possibly be overstated. You'll also want a gate driver smart enough to know when something's wrong. The digital programmable gate driver allows the user to set a lower DSAT voltage, which speeds up detection, stops the overshoot voltage in its tracks, and arrests the peak short circuit current as well. With a dozen or so mouse clicks, we reduce short circuit current by 10% and overshoot voltage by 60%. Often, customers must engage at least 3 different suppliers to get these 3 key pieces. Only Microchip has them all, and only Microchip has unified them to create the total silicon carbide solution for transportation APUs, the ASDAC Plus Accelerated Development Kit. At left, we see the stack up of the SP6LI module, the module adapter board, and the gate driver. Whether the APU uses this common phase-shifted full bridge topology or another approach, it is sure to consist of phase legs. For this circuit, we see how one can take this total solution and drop 4 of them into the primary side of the DC-DC converter. Perfect. And for fun, I show here what a full three-phase implementation of the SP6LI gate driver solution could look like. Microchip has released what we call an Accelerated Development Kit, or ASDAC Plus, that contains the gate driver core and module adapter board, the mounting hardware to the SP6LI power package, and programming kit and adapter. Choose your voltage and current rating, and you're off to the races with your silicon carbide-based APU design. From double pulse evaluation all the way through to system optimization and finally, volume production. We have spoken today about the important drivers of next-gen transportation APUs: power density, efficiency, and noise. Silicon carbide offers disruptive benefits in each of these areas by virtue of its more efficient performance and ability to switch at higher frequencies than silicon IGBTs could ever dream of. We've shown you that the right silicon carbide is here today, with ruggedness, reliability, low inductance power packaging, and a brilliant gate driver that helps you tweak and fine-tune every step of the way. And last, where you've had to put together dozens of meetings to bring these critical pieces together, Microchip has done it for you. We're offering a complete silicon carbide solution to reduce the size, noise, and field failures of transportation APUs. A final parting word. We offer your APU a lot more than just the ASDAC Plus. Visit microchip.com to see how we are delivering total system solutions. Thank you for your time and attention.